So we're going to look at creating a cone via revolution of this linear function around the x-axis. First thing we're going to do is find the volume, but then we're going to take that a couple steps further to look at mass. Now, we know that the volume for a revolution is pi times the integral. This one clearly is going to go from 0 to 5. Because we're going to have this is going to go up to 4 and out to 5, times our radius squared dx. So what we need is a formula for the radius, because clearly the radius is changing depending on where we're at. So if I consider this a y-axis and this the x-axis, I just need the linear function between the two. Notice what happens. This goes down 4 for every 5 it goes over. That means we have a slope of negative 4/5 x and a y-intercept of 4. So our definite integral is going to be 0 to 5 of negative 4/5 x plus 4 squared dx. I'm doing this quickly because we did this last section, but just a couple things to remember. Don't forget the radius has to be squared, and don't forget to multiply by pi. Now, I'm not going to work this integral out in this particular video. The answer will come out to be 80/3 pi, and because I didn't give them here, but these were given in meters, 80/3 pi meters cubed would be the volume of this cone. Now, let's say we had a constant density of 800 kilograms per meter cubed. So this we'll call 2 here. This was part 1. Well, if that's the case, if the density is constant, you need simply multiply it by the volume to get the total mass. So 800 times 80/3 pi is, and you can see this was measured in meters cubed. This is kilograms per meters cubed. If we think of multiplying those together, the meters cancel out. Our answer will be in kilograms. We get 64,000 pi over 3, or as a decimal, it's about 67,020. I'll just 0.6 kilograms. Okay, so the density doesn't vary. Just take your density and multiply it by your volume. What if our density does vary? For instance, what if our density for this cone is given as rho of x equals 400 plus 200 over 1 plus x squared? All right, let's talk about how we would approach this and see what if we can generalize for all of our cones. So I'm going to cut out a slice, and right there is my ith slice. Now, the idea behind this is I'm cutting out the slice so the density is approximately constant on this slice. Now think of what we said before. If the density is constant, you just multiply it by the volume. So if I were going to try to find the mass on the ith slice, well, I would take my density on the ith slice and multiply it by my volume of the ith slice. Now, what would that look like for this particular problem? Well, the density on the ith slice is going to be given by this here. So 400 plus 200 over 1 plus x sub I squared. So that's the density on the ith slice, times the volume of the ith slice. Well, what's the shape of the ith slice? Remember, it's going to have a thickness of delta x. It's going to look like a cylinder, so we're back into the section on volumes of revolution, with a radius r that is given by our function. So pi times negative 4/5 x plus 4 squared. we have the mass on the ith slice. So we can turn this into a definite integral to get the total mass by putting this into our continuous case. So 400 plus 200 over 1 plus x squared pi times negative 4/5 x plus 4 squared. Sorry, we should have had a delta x up here to finish off that volume. It's my mistake, because we'll have a dx here. And to get the total cone, we're going to go from 0 out to 5. Now for this particular video, I'm not going to solve this definite integral. One way we could do this is with technology. The other way is we could multiply this out and do it piece by piece. It's not a terrible integral. For the point of this video, I wanted you to see how it's set up. If we look, right here is our density on the ith slice, and this was our volume of the ith slice. So paying attention to that ith slice will give us this answer. This comes out to be approximately 42,224.8. And now if we think about the units on this, I guess I really didn't give you any. The density was measured in, once again, kilograms per meter cubed. We know the volume was in meters cubed, so this is going to be in kilograms.